That means here things will go base bit stream or symbol stream, whatever it is. Binary. It is a binary interface. BI means is it visible? Okay. Now that means binary interface means that means the source encoder, its source output is a binary sequence. Similarly, that source decoder input, because I have told that these are symmetric blocks in the last class we discussed about, because this channel is some sort of this transmitter chain. This is a transmitter signal transformation chain, I can say, and this is a receive signal transmitter chain. Okay, or rather signal transformation chain. Signal means in a very generic thing actually. So and similarly, that source decoder, it also expects binary interface. That means it expects also bit stream. And that channel encoder or modulator. Okay, so I'm just putting a channel encoder in a very broad perspective. Channel encoder or modulator, what it does, basically it converts this binary sequence, that means a bit stream of 1 and 0, to a form suitable for transmission over particular physical media such as say cable, optical fiber, EM radiation through phase, maybe means water wave. Okay, that means this is my bit stream, say 0, 1, 0, 0, something like that. Here also something 0, 1, 0. So I'm putting 1 because say it will make some error, intentional error kind of thing. It is not that it is exact kind of thing. But this channel encoder or modulator, basically, why the name modulation? Because it has a set of waveforms. That waveforms get modulated or changed depending on the content of bit stream. That means it has its own some sort of a say sinusoid or some waveform. Say sinusoid waveforms, say amplitude, frequency, phase, combination, something, those things, they will be modulated by information carrying bit stream. Because this is my information is coming from source that I want to transmit to the destination from source to destination. Okay. So similarly, so that means modulator actually basically converts the bit stream to a suitable form so that can be transmitted over some physical media. Okay. Now the question is why binary interface? First, then why do I need binary interface for this? I can do completely analog. First of all, that this when you have a binary interface, see all this digital hardware that is cheap, it is programmable. Similarly, this one cheap, programmable. This is the say if you just consider say just cost, this is the simple answer. Okay. And also another thing is that as this is binary interface, this channel, it does not need to know that whether actually this bit stream is coming from some JPEG image or whether this bit stream is coming out of some song or whether this bit stream is coming from video. So he doesn't care. He only knows that I have my interface, binary interface. It's a bit stream. I will do some processing on it and I will convert that bit stream to a form which can be transmitted over my channel. That's it. So that means your source encoder, source decoder, media means the type of whether it is signal, image, video. So that sometimes we say media actually. This channel encoder, channel decoder, the corresponding processing over here, that is independent of the nature of the media. Please try to understand. Because whatever may be the type of the media, finally they will give you the bit stream. So that means depending on the media, I have to change this channel encoder block. That is not required because I am finally getting a common bit stream, and where from this bit stream is coming, I don't bother. Okay. That means this source encoding and decoding that can be done some sort of a independently of this block. Okay, I can change this one, and I can change this one independently and see the performance. Say when I am doing some sort of a JPEG, and say I am doing a compression kind of thing. I am doing JPEG 2000, and I am trying to see, okay, what is the effect. There is no such special effect for this one from this perspective. That means optimization can be done in an isolated way. So that means irrespective of the right position. Okay. So now let us so that means first the basic point of the digital communication. See, try to understand. The digital communication means we are basically the data communication, digital communication means basically we are interested in this portion. Okay, where my input is a bit stream, output is a bit stream. Okay, now depending on the media, if it is a video, I will use MPEG source encoder. If it is an image, then I will do a JPEG source encoder. If it is some sort of a just a file kind of thing, then I will do some sort of a WinZip or say tar or this type of one. So that finally I have a bit. So communication block understands that my input is bit stream, output is bit stream. That's it. And the source encoder, source decoder, they are chosen depending on the nature of the media, whether it is image, video, voice, whether it is speech, music, because speech and music has different aspect actually, because the spectrum is different. Okay. So that is most important, this binary interface at this point. Okay. So now let us break this source encoder and source decoder portion. Okay. Is this philosophy clear? That means what we are going to study?
Yes, sir.
Raju Karmakar 24 declined the class. I don't know why. So now let us zoom this block, because first I like to give you some sort of a top level view, then we'll move in individual block and we'll discuss. Otherwise, many a times there's a chance that that you may be lost about your position, because okay, it's about your what you are studying, where are you. So now the next is say mine. That means sorry. This is my input waveform. Input waveform means input media, whatever you say. Means waveform means waveform. I am just using a very.
Can you please shift the page a bit right?
Is it okay?
Yes, fine.
Input waveform means input rather media, because waveform, though we say waveform mainly a time domain signal and all that, but it is an input media. Now I know I have a source encoder. And then I have a binary interface. Similarly, I have a source decoder. And finally, I have an output waveform. Okay. This is my binary interface. Okay. Now I am just breaking it. This portion at this point we are not talking about this portion. Okay. So mainly in digital signal processing, digital image processing, these that basically you are talking about you study this portion basically. Source encoder decoder side. On the source, that means you are doing transformation on the source information. Okay. Now here we are talking about mainly, we will talk about mainly the ports we are talking about that are this side of the block. Okay. Now rather source encoder means I will break it into 3 different blocks. Similarly, decoder is also because it is symmetric. Okay. Now 1, 2, 3, 1 prime, 2 prime, 3 prime. Means here I am doing just an input waveform, just I'm not. Now this one, first one is some sort of a, okay, I'm talking about say see, okay, let me write. Then sampler, quantizer, and discrete encoder. Discrete encoder. Okay, and the output is binary interface. Now this, so similarly if it is discrete encoder, then this will be discrete decoder. Just 1 minute. If it is possible, can you move the camera a bit behind? It's out of focus. Just wait. Just let me. Is it going to be better? Because this focus is means it's this Logitech webcam. I don't know whether focus can focal length can be changed or not because I don't have that option. Just 1 minute. I don't find anything over here to change it. No motion, nothing. Is it better with the sketch pen?
Yes, sir.
Actually, with sketch pen, my flow disturbs. Actually, the point is there only. Anyway. This one, say, I am assuming this one is for the time being input, say, analog waveform, say speech signal. Just to make life simple. Okay. Now, some sort of an analog signal. Okay, because source encoder, it depends. Actually, that I told that if you can remember the previous one, I told the source encoder, this choice of source encoder it depends on the nature of the source. Okay, these two are tied. Okay, so here I am assuming some sort of a say speech signal or some analog signal. So I have the input waveform, that means input analog waveform. I have a sampler, and some sort of a that ADC is first step. You quantize, and after quantization, what do after quantization? You generally map to the nearest point. That means, say, if if your range is 0, 0.25, 0.5, 0.75, 1, say if you have some sort of a 0.72, then basically you map to the 0.75. Okay. Now, so that means here if you just sample means you may get 0.725 or something like that. Now after quantization, you map to 0.75. Say something is 0.93 means you will map to 1. Now after this 0.75, 1 or 1.25 means 0.25, for each one you have some sort of a bit stream. Okay, you have generated. That means if I have a 0, then I will have say 80 or say 40. If it is 0.25, then I have 30 and 1. If I have 0.5, then say 2021, like that. If I have 0.75, 30, something like that. You have this combination. So that we say that is my known mapping, some sort of a discrete encoder. And finally, I am generating some bit stream depending on the signal. Okay, so that means this is my binary interface. Say you are generating some 0, 0 like that, continuously you are generating. So similarly, when I am getting this bit stream from the receiver side, from the channel decoder, I will put it into the discrete decoder. That means I will this is, I know that each one is 4 length sequence, so I will just this 4, then I will take next 4 and all these things. That is a discrete decoder. Depending on this, I will check 000100 means actually 0.75. That I have a lookup table. LUT means lookup table. Okay, 1000, that means it is something 1.25. Something I have a table. So I have some sort of discrete values. That means after this lookup table, if you see that, please remember this sequence, this is some sort of an analog sequence. This is analog sequence. Okay. And after quantizer, this is called symbol sequence. Okay. Symbol sequence means it's a series of say 0.75, 1.25, 0.5, 0, same thing, 1.25, all this. So this is a symbol sequence. Okay, and from each symbol you are getting some sort of a 001, 010000, and you have decided, okay, so my depending on the dynamic range of the signal, I with 4 bit I am okay. I don't have all negative part. So with negative part means you have to again put up some sort of a MSB sign and all these things. So I am not going to that. I have all positive side signals, make the life simple. So I have this. Sometimes, please remember, sometimes this is also called symbol sequence. Sometimes this is also called symbol sequence. Okay. It depends. It depends on the context actually. Okay. But anyway, but these two are basically same. When you have some idea that basically whether it means this mapping, when you have the lookup table, that means you always know that this means basically actual value is how much. This actual means in some 0 to 0.5, 0 to 1.5 or 0 to 2 in that scale how much. 0010 means how much. 0100 means how much. If you have the lookup table or all these things. Now, this analog sequence, if you see at this point, what you have, that means you have taken either, so these values will be either 0.5, 0.75, 0.25, all these things. So that means this one, at this point, you have a staircase type of one. Okay. But you want your analog signal, actual analog signal is some sort of a more natural kind of thing. That's why you put an analog filter so that it will be you are making little smooth at this point. So this point, it will be little smooth with some error, with some quantization, because you are doing quantization. So you cannot come back to your original one actually. Okay. So this is so that means this is my analog sequence. This is my symbol sequence, and this is my bit stream. And this bit stream that is going to feed. It will be fed to the channel encoder. Channel encoder will transmit. Channel encoder will transmit through the channel. Finally, through the channel decoder, you will get a bit stream. Bit stream 2. So that means this whole portion is some sort of a source encoder decoder. This is my source encoder AC, and this is my source decoder. Please remember, for analog signals, for continuous time signals, continuous time signal. If you have some sort of a analog, means if you have some sort of a old analog camera, so you also have same thing, only not time, it is space and all these things. Okay. Now, these symbol sequence, this an analog domain symbol sequence in this one. Okay, because I told that many times this one also used as a symbol sequence. Many times we say this symbol sequence, that this is called information sequence, because that is the core information. This is not the core information. The information is carried on this means analog values, okay, or symbol values, or on this bit stream info sequence, or sometimes we say it is a symbol sequence. Okay. So that means this is top one is my source encoder, the bottom one is my source decoder.
Hello, sir.
Yes.
Sir, what's the work of lookup table if we have already the information sequence before that? So information sequence is something like 0.75, 0.25, right?
No.
Then?
Actually, this discrete decoder and lookup table, they are basically same thing. Actually, they break it in that way. Basically, that you get this bit stream, what discrete decoder does. Discrete decoder first, say, I am giving you some sort of a 16 or 17 bit stream. You have to find out where is my boundary. Okay. That means, see, you try to understand. Say, I have given something like that. Whether my bit stream starts from here or whether my bit stream starts from here, there may be initial garbage. So I have to find out those things, and this is called some sort of a discrete decoder. You're getting my point. All this, so, and also that means, oh, finally discrete decoder find, oh, this is the point. So that means from here you have to take this 1 0 0 0, then you have to take another 40, then in this way. Okay, after some time, so you cannot just run it continuously once you have made it, because in the meantime there is some error and finally there is some garbage in the bit stream. So periodically you have to do this. Where is my thing actually? Where the thing will start, where the actual information will start. Those things actually done by basically discrete decoder. And basically discrete decoder and lookup table basically does what? This finally I know that this 1000, then lookup table will convert it to the 0.75, 0.25, all these things. Okay. Basically these are done in only one function. Actually all three are in one function. Are you getting my point?
Yes, sir. Thank you.
Okay. So basically, see, it is discrete. Actually, it should be discrete decoder and lookup table kind of thing. Actually. So anyway,
Sir, lookup table has a separate hardware, or is it something like?
no, it's an array.
Okay.
Lookup table is always software. Yes,
Okay.
you can keep it in FPGA. Then now, lookup table is an information. That means it is in an array. I have kept it. 0.75 means 1000, 0.25 means 0, or say 0, and all that information you are keeping it in lookup table.
Okay.
Is it okay?
Yes, sir.
So now here we are talking about in all software business. Here we are not talking about hardware. Okay, if something hardware, this analog filter also you can, analog filter may be software, absolutely software analog filter. Okay, so analog filter does not mean that you have to do some sort of say maybe you are doing the basic filtering in digital domain and finally you are just converting it to a DSC. That also you can do. Okay. So, or sometimes you may feel, no, I will do it, all that component, op-amp and all these things, I will do it. Oh, fine, do it. So means I'm not talking about this component wise, this analog hardware, digital hardware, I'm not going to that details, okay, at this point. Okay. So now, so is that overall some sort of a source encoder, source decoder clear? Means in a very rudimentary way. So now let us move to the source, because I have what are the component? I have a source. Sorry. I have a source. I have a source encoder. I have a channel encoder or modulator. Then I have a channel. Then I have a channel encoder or modulator. Then channel decoder or demod. Then source decoder. Then your destination or rather decoded source, whatever you say. Okay. Now let us talk about a little bit of source. Now, so the source, first of all, we are talking about, say, discrete source. So first of all, the source may be discrete, source may be also analog. Okay, analog source, you know, you are talking, say, or microphone. So microphone is taking analog signal. That is analog source. That means your mouth is an analog source. Okay, voice over microphone or output of a sensor. Okay, maybe in sequence of means analog camera images. So these are sources. Now let us talk about discrete source, because analog source means you are it's confident. Now discrete source means, what do you mean by discrete source? That means it generates the discrete symbols. That means, say, a source which is generating letters from English alphabet. Okay. That means what is the variation? The source variation. Source variation is only 26 letters. Okay. I'm not talking about capital, small, and all these things. So 26 different output only it can generate. Or say binary symbol from a computer file. Okay. So that means it can give only 0 and 1. So that means the variety of the output that is limited. Okay, means number of discrete output of a number of output of a discrete source is fixed. Okay, but if you assume a source as a sinusoid source, the number of output, that means number of different amplitude level, that is infinity for a continuous time signals. Okay, because it's a continuous value function of a time, space, whatever it is. So that means the discrete source means letters. So say that means discrete source means I am telling you I will you can only utter the letter of English alphabet. So you can only say 26 letters. Nothing is allowed. Then and that actually, see, the idea is that I like to transmit this information to the other part. Okay. So the destination, he is interested whether you have said A or Z or C or PU, something like that. So that means then it is some sort of, you are basically you are sending a discrete source, discrete symbols. Okay. So letters of English alphabet, okay. Or maybe binary symbols from computer file. And analog waveform is some sort of a voice over microphone output of a sensor. And the idea is that whatever be the nature of the source, the output from the source is modeled as a sample function of a random process. This is very important. See, I'm just please try to understand. This is Shannon's view. Okay. Whatever be the nature of source. Okay. I will just assume the output of the source is modeled as a sample function of a random process. That means whether you will say A, B, C, D, it is your output is the output of a distribution. Probabilistic distribution. That means some sort of a distribution that you will say with 0.1 probability you will say A, with 0.01 probability you will say B, and finally what you are saying, some sort of a, say you are saying A, Z, B, C, D, F, O. So it is basically a realization of a random function, random process, and with this much probability. Okay. So this is the Shannon's view, and the set of possible source output, that it is that means this rather than any particular output is of primary interest. That means what are the possible source output that is of interest, not that a particular, because in a probabilistic process. So are you really interested in say some sort of a zero mean Gaussian random variable? Do we do anything about individual realization? We don't. We always talk about mean, variance, median, these, that means all statistics we are talking about. We never talk about instantaneous. So here also, that the digital communication, mainly Shannon's view is that we will mainly talk about that what are the possible source output and signal in such a way that this possible transmitted signal can be best distinguished at the channel output. So please try to appreciate my point. Transmit each possible source output, each of these 26 possible source output, say, into a transmitted signal in such a way that this possible transmitted signal can be best distinguished at the channel output. Okay. So that means that I have, see, 26 symbol with say some space symbol also, because otherwise just say 26 7 symbols, and 27 symbols means I can code it at a 5-bit block, because 5-bit means 32 different 5-bit block it can be, means all 0 to all 1. Okay, it's 2 to the power 5 32. So that means, but I have only 27, so it's okay, because I cannot go to 4-bit block. And if you consider uppercase, lowercase, some special characters, then you have to take the 8-bit block kind of thing. So that means this 8-bit block means 8-bit some 0010 kind of thing you are continuously transmitting. And the channel, first of all, channel, that is, as a communication engineer, channel is not in your control. Okay. Not under the control of a digital designer. And it may be digital channel with binary input and output, maybe 4 kilohertz voice channel. That means 4 kilohertz voice channel means with telephone where you are talking about, that is an analog channel. Maybe a coaxial cable channel with bandwidth restriction. Okay. So that means, first of all, the channel is not in your hand. Okay. Now, means channel statistics. Okay, you only have some amount of information. Don't expect that somebody will give you channels transfer function so that you will get the channel out like that. Channel is also probabilistic. Okay. And channel is a noisy channel. You have to understand that. And the channel encoding, I told, channel encoding is a modulation and channel decoding is a demodulation. That means the modulation means what? Modulation means, in a sense, it is multiplying the low pass signal waveform into high frequency sinusoid, thus placing the signal waveform in a frequency band suitable for transmission and regulatory requirement. This one is, I will finish it here. That, so source we have understood. That means source, if it is an English alphabet, then it is 26 plus 1, 27. That means 27 means 16. With 16 different this thing we cannot do. Some sort of I have to take 5-bit some kind of block, so that means all means 27 means five different 5, because I have a 32 different symbols. 5 symbols will not be used over here. Okay, means A to Z and a space. If it is your means uppercase plus lowercase, that means 26 plus 26 52 plus some sort of a special characters, that means all this ASCII if we talk about, then plus some, if you just consider that ASCII, if you just check that ASCII table kind of thing, then generally we means we cannot do it with 6 means it is more than 64. That's why sorry, more than 128. So that's why you need a 8-bit block. Okay, that means it is 8-bit. Why when do you need 8-bit block? When your number is more than 128 and less than 256. Okay, means 128 to 255 kind of thing. Okay, so you need a 8-bit block kind of thing that you are transmitting at the channel, and channel output should be as distinguishable as much as possible. Now I told that channel encoder. Now this is about source. Okay, so we will again come to the source and all these things. Now channel encoding means, I told that it is a modulation, right? Means next block. Please try to understand. This is input. I have a source encoder. Then I am talking about a modulator or channel encoder. Now I am talking about, this is a binary interface. This is a source decoder. Output, say CE, channel encoder or modulator. Okay, because channel encoder is, okay, we will discuss that later maybe. Channel encoder, there are some specific channel decoder or demodulator. Okay, and I know that Now I'm talking about channel encoder and modulator. Channel encoder and modulator means what? I told I have a binary interface BI. Now I will convert this bit stream to a suitable signal which can be transmitted through the channel. Okay. Now let us talk about in a well-less communications point of view. Say I am assuming this is my very low pass signal. Say some sensor output, some RTD's output. Okay. Say because at the temperature is a very low frequency signal that you want to transmit. So you have to do multiply the low pass signal, this RTD output, this waveform, with a high frequency sinusoid. I told that high frequency sinusoid I will generate over here. I will multiply that with this high frequency sinusoid. And so that if you multiply with the high frequency sinusoid, what will happen? It will just move to that spectra. Do you get it? If I just multiply with some sine omega t, and if I have a low frequency spectra, I just break it into sine omega t plus sine 2 omega t, sine 3 omega t, sine 4 omega t, and if you multiply sine omega 0 t with everyone, then multiplication of 2 sine means sine cos whatever it is, that means frequency will be translated. Are you getting? Sine AB means sine A plus B plus. Do you know this formula? Hello.
Yes, sir.
So if you means say, could you remember that sine A plus B plus sine A minus B is equal to something to sine A cos B, all these things. So that means if I just take it from a different perspective, say cos B, it's a low frequency signal, okay, and sine A is my very high frequency channel signal. So that means what will happen? Sine A plus B and sine A minus B, that means A is a big. So basically your B component is actually shifting on top of A. Okay. So that means if A is 1 gigahertz and B is 1 hertz, that is 1 gigahertz plus 1 hertz and 1 gigahertz minus 1 hertz, something like that. It's coming. So, and basically channel encoder is doing that. Basically you have a 1 hertz signal and you are generating 1 gigahertz. If you multiply that with sine and cosine, because these 1 hertz, it may not be sinusoid, but you can do a Fourier kind of analysis and you can break it into different frequencies. And you are taking my carrier is a pure sinusoid, 1 gigahertz. So that means it is 1 gigahertz plus 1 hertz, 1 gigahertz minus 1 hertz, 1 gigahertz. Say it is all odd harmonic, 1 gigahertz plus 3 hertz, 1 gigahertz minus 3 hertz, all these things. So that means multiplying the low pass signal waveform with the high frequency sinusoid, thus placing the signal waveform in a frequency band suitable for transmission and regulatory requirements. So this channel may not transmit, channel has a spectrum. Okay, channel has a frequency response. Okay, channel may not transmit 1 hertz. Okay, there are channels. If you just go to plot of the channels 1 hertz. At 1 hertz, the response is very poor. Okay, but channel can transmit at 1 gigahertz level. One is 1 gigahertz nearby there. There the board again is very high. Okay, so then you are going to that 1 gigahertz plus 1 hertz, 1 gigahertz minus 1 hertz, all these things. Modulator does this thing and channel can transmit this one. Then you do that again frequency translation. So remove that 1 gigahertz portion, again multiply with 1 gigahertz signal and get that one. And finally again you will get some all 1 hertz related business. Okay. Now basically here see, try to understand, this is my binary interface. After 1 hertz you have to, what you have to do, then you have to again convert to the bit stream. Here it is bit stream, send this bit stream here, again source decoder, from there this get the signal over here. Okay, so it's maybe at this point you just take this portion, means don't talk about okay 1 gigahertz, then it is sinusoid, it is coming. At this point try to get the philosophy. I will explain everything in detail. Each of the block I will explain in the next few days. Okay, So basic idea is that modulator is basically doing in a wireless communication. You have some information at low frequency. It will just take the spectrum. It will uplift the signal, frequency uplift to the signal which is amenable to channel, and then again it will down translate and it will give it to your all Hertz level thing and you get the output. Philosophically, it is like that. Modulator does this thing. That why the 1 GHz is coming into picture? Because say your regulatory requirement is something like that. That it is told that yes, you can only allow to transmit at 1 GHz. Nearby that 1 GHz plus minus 1 MHz in that range. No other band I am not giving you. Okay. So you have to do that. So that means though you have a 1 Hz signal, but you have to take it to that level in that 1 GHz plus minus 1 MHz in that band, and you have to do these things. So modulator does this conversion. Okay, so that which is amenable to channel and regulatory requirement. Now another thing, just for the time being, this generally we talk about this low pass signal. Low pass signal or low frequency signal, whatever we say. Generally we say baseband, and the high frequency signal or high frequency, high pass, high frequency, whatever it is, that we say the high frequency sinusoid or this, that we say RF carrier or high frequency RF carrier. So let us finish over here, then we'll start tomorrow at this point. Okay, thank you very much.
Hello.
Yes.
Yes, sir. What is that BB?
Baseband.
Okay.
Oh, thank you.
Excuse me, sir.
Excuse me, sir.
Yes.
Sir, some of us have joined this course yesterday only. So, if possible, can you please send us the invitation again?
Okay. I will take this one, because then I have to send the invitation to the whole web, because in the ERP that their names are intermingled. So I have to take the again invitation to all, because I don't know where their names are present and all these things. Okay. Okay, thank you very much.